It's time to start. And today's speaker is Georgy Ryabov with the talk devoted to stochastic flows on metric graphs. Please, Georgy.
Thank you for the introduction. So in my talk, I will review some general approach to constructing stochastic flows and uh, give some applications to stochastic flows on metric graphs. And also, I will pose some open problems. So let's start from the definition of a stochastic flow, which is well known. Um, I'm sorry. Okay, so we will work in general in locally compact separable metric spaces. And a stochastic flow is a family of random mappings of the space. I will assume that it is measurable in all arguments, satisfies evolutionary property, which means that the composition of two mappings psi rs and psi st is equal to psi rt. So the distribution of psi st depends only on t minus s, and the mappings act independently on disjoint segments. Stochastic flows are usually described by their endpoint motions. So if psi is a stochastic flow, under some mild conditions, the function p and t, which acts on f by taking expectation of f from the values of the flow. So this function, it occurs to be a transition function, and also under some mild conditions, this function is a failure for each n, and between themselves, these functions satisfy some consistency assumption. Okay, and also we will assume the following property of P1, which actually means that we will work with the flows with continuous trajectories. If we start from such sequence of transition functions, then it is hard to construct stochastic flows that satisfy this evolutionary property 2 without exceptions. However, it is well known that one can construct a stochastic flow phi that satisfies a weak evolutionary property, which means that this equality holds almost surely where the exceptional set depends on, in general, on R as X. And, yeah. In order to construct such flows, I will need a quite strong assumption. So let us fix a countable dense set D. The assumption is the next one. So for any compact L, this is a compact in a product of time and space. Yes, for any compact L, we look at all trajectories from this weak flow that at time s were in this compact L, and we look at restrictions of these trajectories after time s. So this set of restrictions must be relatively compact. So we will have this assumption. So next, for points Sx and t bigger than s, by kst epsilon x will be the closure of trajectories of the flow on the interval from s to t that were at a distance epsilon to x at time s. Okay, and by our compactness assumption, this set is compact, non-empty, and hence we can take intersection in epsilon, and we will get a compact set KSTX. The intuition is that this set KSTX is all possible limit points when we take only the part of the flow that started from the dense set and that approach x at time s. Okay, and one more notion. So nu STX will be the number of points in KSTX. Okay. Now tau Sx, it is the smallest time t after s, such that on the segment St we have at least two possible limit points. Okay, and by the set of bifurcation points, I will denote the set of points as x, such that tau Sx is equal to s. Okay, so it means that immediately after time s, there is a possibility of getting two limits for the trajectory of the flow.
Georgi, and is this
Yes.
random set?
Yes.
Is it measurable? So is it possible to prove that this set is measurable?
It is possible, but it is hard.
Oh, okay.
And actually, yeah, okay. So the first observation is if time t is less than this moment tau, then the set KSTX contains a single function, which in fact is a modification of the trajectory of a weak flow. And regarding this set B, since first of all, it is random and it can be of complicated structure, and actually we don't know much about this set B, so I will just assume that F is some deterministic closed set that almost surely contains B.
Can it happen that this F coincide with all product R multiplied by M? Okay, good.
Yes, yes.
Mhm.
Okay, and now the idea is the following. So this new flow theta may not satisfy the evolutionary property at the set of bifurcation points. So what I will do is I will look at times when theta hits F, and at these times I will just reconstruct it so that we have the evolutionary property. Okay, so let's consider a point Sx. So sigma with index k plus 1, yes, it is the first time after sigma k, such that that started from zk. So zk was a point where the trajectory hits f. Okay, so and sigma k plus 1, it's like the next time of hitting f. And zk plus 1, it is a point where the trajectory hits f.
But is it possible that sigma k plus 1 is equal to sigma k?
Yes, and look at the next definition.
Mm-hmm.
So ksx, it is the first index when sigma k equals sigma k plus 1.
Oh, okay.
Maybe k is infinity. I mean, maybe ksx is infinity. And let's note that if ksx is finite, yes, then after this moment, sigma becomes constant, and that also becomes constant. Okay, and let sigma infinity will be the limit of sigma k. It can be also finite or infinite. And if ksx is finite, then this limit is just sigma at time ksx. Okay, and now let's construct another flow psi. And according to the idea that I already explained, okay, psi stx is defined as parts of trajectories of the flow theta between times when they hit the set f. And after this time, sigma ksx, assume that it is a finite time, then the trajectory of psi simply follows the trajectory of theta. We have also to consider like the third case, but I will give assumptions that that doesn't happen. So and we note that this new function psi sx is defined for all t greater than s when ksx is finite. Okay, now the result is the following. So assume that almost surely all these indices ksx are finite, and if ksx is 0, then the trajectory theta immediately coalesces with some trajectory phi, out of which we constructed theta. Actually, this theorem was already discussed, so I don't give a proof. I can only spell the idea that between times of visiting f, we have the evolutionary property like by definition, and at this last time sigma ksx, we have immediate coalescence with the trajectory phi. The next observation is that instantaneous coalescence property immediately gives the conditions of theorem 1. So what is this instantaneous coalescence property? We take two moments of time, s less than t, and look at the values at time t of all trajectories from the flow phi that started before S. So the property is that this set must be locally finite. And instantaneous coalescence property makes theorem 1 like obvious because we just take F, the whole space. Then actually these moments ksx are equal to 0 and psi coincides with theta. So under this instantaneous coalescence property, theta is already a strong flow. Now, let me recall a sufficient condition for instantaneous coalescence property. When we have 2 points x and y, then by tau I will denote the meeting time, and for a compact k, by sigma k, I will denote the time when trajectories left the compact. Okay, so a sufficient condition is the next one. So assume that for any compact k, there are constants, 5 constants, such that the product of alpha and kappa is greater than 1. So what is alpha? Alpha stands for like the power of the meeting time. The condition 1 means that if the distance between points is less than epsilon, then the probability that two trajectories didn't meet before time, which is proportional to the distance to the power alpha, is bounded, is strictly less than 1. Yes, for all x and y from k.
Georgi, could you please repeat where is kappa in Formula 1? Is there kappa in Formula 1 or not?
There is no kappa.
There is no. Thank you.
It is in 2.
I see. Thanks.
And kappa is related to alpha, like alpha kappa is bigger than 1. So kappa like stands for geometry of the space. The condition 2 is the following. If a set A contains at least n points, then for some 2 of them, the distance will be less than 1 over n to the power kappa. Okay, so if these 2 conditions hold, then the set of the set phi RTY, yes, where trajectories started before time s, will be a finite set. Yeah, so here is also additional assumption that these 2 trajectories didn't leave the set K. And this condition is useful in the case of metric graphs, because for a metric graph, we have kappa is equal to 1. So now, as an example of application, assume that these trajectories phi, they are independent before meeting Walsh-Brownian motions. Okay, so now let us assume that M is a star graph. For these trajectories, instantaneous coalescence property holds because on a star graph we can prove, and actually we already proved it, that the probability that the meeting is less than beta to the distance squared is bounded from 0 for all points in the. The result is also true when M is not a star graph because these two conditions, they are local conditions, and in the neighborhood of each point, any metric graph looks like a star graph. Okay, so I'd like to mention an open question is to study clusters in such flow. By a cluster, let's say that 0 is a vertex of a star graph, then a cluster CT is a set of all points X that coalesced with a trajectory started from 0 at time t. And it turns out that almost nothing is known about the distribution in some sense of this CT. So is it a connected set or not? How boundaries behave? The only studied case is the case of Aratia flow. Okay. Now I want to go to other examples where we don't have the instantaneous coalescence property. Okay. And the first such example is the so-called Burdzy-Kaspi flow. We will consider the stochastic differential equation for this cube Brownian motion on the real line. So here W is a Brownian motion, L is the symmetric local time of X at 0. Okay, so it is known that there is a unique strong solution of this equation. Okay, so we can construct the transition functions Pn and the corresponding weak stochastic flow. Okay, now with each trajectory phi, we associate its local time and define the process W as that trajectory phi minus initial point and minus beta times local time. So W is a Brownian motion. And it is important that these processes W, R, Y, they all have the same increments. Now, as the set F, we take the product R times 0. And now I will show that with probability 1, these indices KSX, they are almost surely all less or equal to 2.
And what does it mean? That twice you can not coalesce or what?
You can hit 0 and like spend some time not at 0 at least 2 times. At most 2 times.
At most 2 times.
Yes.
Thank you.
Okay, so now let this, so assume that k is greater or equal to 3. Okay, so then the corresponding trajectory of the flow starts at point X, then hits 0 at sigma 1, then it is not 0, then it hits 0 at sigma 2, then it is not 0, and then it hits 0 at sigma 3.
Georgi, and sigma is the next hitting?
Yes.
Because if you fixed S and X, then with probability 1, sigma 1 is equal to sigma 0. But I'm not sure that, but for...
X is not 0.
No. I mean, even if X is not 0. So sigma is the next...
No, sigma 0 is S.
Sigma 0 is...
Sigma 0 is just the initial time, and sigma 1 is the first time of hitting 0.
Oh, I mean that if you fix S and X, then sigma 2 is equal to sigma 1 almost surely. Is it correct?
Yes, but we need it almost surely for all S and X.
Simultaneously, yes?
Simultaneously, yes.
Mm-hmm. And you prove that probability of this event is...
Yes.
Oh, okay. Thank you.
Yeah, but okay, now what it means? It means that like between sigma 1 and between sigma 0 and sigma 1, let me like, so this is 0, 1, 2, and 3. Between sigma 0 and sigma 1, our trajectory is not 0. And it hits 0 at sigma 1, so W of sigma 1 will be equal to WS minus X. Okay? Between sigma 1 and sigma 2, the increment the WT minus W sigma 2 is not 0. And it hits 0 at sigma 2. And the same between sigma 2 and sigma 3. At times sigma 1 and sigma 2, W equals WS minus X. And it remains to note that the picture that I draw is impossible because otherwise Brownian motion has a point of decrease. But Brownian motion has no points of increase or decrease. This means that at 1 we will actually have something like this. And the same for sigma 2. We can make a conclusion that the Brownian motion has two local extrema at the same level. And it is a result by Tanaka that this is impossible.
Georgi, can you explain again which conclusion you can have from this structure of the Wiener process about to applying to your stochastic flow?
The conclusion is that the flow, the trajectories of the flow cannot hit 0 like at 3 separate times.
But we already have some information that these trajectories are like diffusions, yeah?
Yes.
So this is not property of the flow. This is a property of one trajectory. Am I right?
Well, it is a property of Brownian motion W. Yes.
Yes, exactly. So my question is why we have to consider this property in application to stochastic flow? What is going? How we will use this property, or what conclusion we can make from it?
You mean from this result?
Yes.
We will show that it has a strong
What we can
modification.
say about stochastic flow from this?
The stochastic flow has a strong modification.
Why it has a strong modification? We avoid some bifurcation points, yeah? Or what?
It has a strong modification because the constructor that we presented was to indeed to avoid bifurcation points, which are all in this set F. Yes, and we construct modification like by reconstructing trajectories of the flow between hitting the bifurcation points.
And this was between hitting the bifurcation points means that single trajectory have just one bifurcation point or what? What does it mean between bifurcation points?
It means that if theta is a weak flow and we define psi as a part of theta between kth and k plus first time of hitting the set of bifurcation points.
Okay.
So it will have a strong flow property.
Can you draw a picture where this f of special form like r multiply on 0 also will be drawn?
Well, I will have another example on a metric graph.
Okay.
Okay. Because my pen is not working well. And one more case we have to consider when k as x is equal to 0. In fact, this case was considered in the work of Burdzy-Kaspi. Actually, they proved that the trajectory theta s that started from 0 also has the form like wt minus ws plus beta lst. Moreover, this L is a local time of this trajectory, and if this local time is 0, then the local time, like for all trajectories that approximated theta as 0, is also 0. It means that the Brownian motion, okay, so k is equal to 0, so trajectory starts from 0 and starts immediately hitting 0. It follows that the Brownian motion hits the same level infinitely often, while its local time doesn't increase. So this is impossible. As a consequence, the local time of this trajectory that starts from 0 is positive. But in this case, again, Burdzy-Kaspi proved that the trajectory immediately coalesces with one of the functions phi. Okay, and
Georgi, and in Burdzy-Kaspi flow, I remember that they proved that they call it triple points, that with probability 1, I think 3 trajectories can coalesce.
Yes, as I remember.
Is it a contradiction to the definition of strong flow or not?
It is not a contradiction because they didn't consider a flow. So they considered only a flow that starts from a countable set.
Yes.
And then they took all possible limits. So it is not a flow.
Okay, but can you construct a strong flow?
Yes.
And will this flow
it will be
same
contained
properties?
It will be contained in their flow.
And triple points also?
No. In my construction, no.
Okay.
I avoid them.
Okay, thanks.
Okay, and one more example. This is a Tanaka equation on a star graph. Okay, so we have a star graph with d edges. P1, PD are the transmission parameters. And the Tanaka equation on M is defined as follows. So here f is a like smooth function which satisfies this condition. F is a function on the graph, respectively. Fj is its a restriction to the edge ej. Okay, and to each vertex we associate a sign, plus or minus 1. The solution to this equation, along edges, it behaves like W or minus W, depending on the sign of the edge. And it turns out that it is relatively easy to show that such flow will have a strong modification. As a set F, we take the product R times 0. So here 0 is the vertex of the graph. And consider the mapping G. It is a mapping from the graph onto the real line. G of x is a sine of x times the absolute value of x. The point behind this construction is if we apply the mapping G to the weak flow phi, we will get a weak Burdzy-Kaspi flow on the real line. And then it immediately implies that almost surely indices k as x are less or equal to 2. And if k as x is equal to 0, then it means that x is 0, sigma 1 is equal to s. And as Burdzy and Kaspi proved, the local time at 0 of the trajectory from the Burdzy-Kaspi flow is positive. And then they also proved that the set of values of trajectories at time t will be a finite set when they are close enough to 0. So then we get a strong flow modification for the flow of solutions of Tanaka equation on a star graph. Okay, and the last I want to mention is an open question. Can we do the same thing for an interface SD on a star graph? So this is an SD of the following form, where Wi are independent Brownian motions associated to edges of the graph. And when the process X is on the ith edge, then it is driven by Wi. So this is all I wanted to present today. Thank you for the attention.
Okay, thank you for interesting talk. Maybe someone have questions or comments, please.
Ingrid, I have a question about this open problem. So you
Mhm.
would like to construct a strong flow with these particular Brownian motions or with some Brownian motions, but that have the same properties, similar properties.
Mm, well, I don't think that we have any Brownian motions in the flow
Mm-hmm.
because we start from distributions of endpoint motions.
Yes.
So the flow must be such that you have this W. Yes?
Yes, like in this example too, I find W from the flow.
Yes, exactly.
Yes.
Uh-huh. Uh-huh. Yeah, because sometimes Tanaka equation does not have strong solution, but
Exactly, yes, exactly.
okay, thank you.
Okay. I also have several questions. The first one is about this construction of the flow related to Tanaka equation. Because you see, maybe it is good to look at the paper of Pavel Chernega in Ukrainian Mathematical Journal, which we produced it when he was doing attempts to be my PhD student, about the total local time for Aratia flow at the point zero.
Mhm.
It occurs that it is finite. So I think it can be useful in your construction too, at least to look on this functional, or maybe have some conclusion from this finite finite value of this total local.
Mhm. Yeah, maybe yes.
Mhm. Okay, and the second question is, you construct this flow, at least under some conditions. What do you think about the existence of the dual flow in the backward time under these conditions?
It is a question under consideration, and
Mhm.
the first idea was that probably the dual flow will be not a flow of mappings.
Mhm.
Like,
Because of what? What is the main reason?
because like in the Tanaka equation, when we hit zero, yes, everything between two the trajectories goes to zero. Yes.
But you see, maybe it can contain annihilating particles. Maybe Oleg
Maybe yes.
can continue this discussion. Yeah. It looks like even if we have bifurcation point, we can produce something. The dual flow will contain some annihilated particles.
Yes,
Oh, yes.
it is very.
Yes, if the dual trajectory is trapped.
Yes, exactly. Yeah.
Mhm.
Oh, very interesting.
Okay, maybe some other questions, please. If not, then Georgi, thank you again. And
Thank you.
Katerina, maybe know who will be the next speaker.
The next speaker will be Katerina Glinina.
Okay, let's see something about point processes. Okay, for today that's all. Thanks everybody and see you next week. Bye.
Thank you very
Okay, see
much.
you.
Goodbye.
Bye. Bye.